So today I want to talk about a rather. I think for me I feel it's boring, but apparently it's very important. So basically, classical mechanics again. Classical mechanics. So here, uh, the thing is, there is this thing called Lagrangian. I have done this in a video, like a little talk about what this thing is. But there is also another thing called Hamiltonian. So you can say this as a twin brother of Lagrangian. So sometimes we like to use this, sometimes we like to use this. Both have their benefits and both have their own cons, you can say. Today I want to talk about this one now. And actually, honestly, this one just was a just cheap ripoff of this one. Like, I mean, this one was made from Lagrangian. Like, this is kind of uh, it's a rebuilding of a Lagrangian. Like we altered Lagrangian, we just wanted we adjusted Lagrangian according to our needs and got this thing. This thing is mostly used in the idea of this. We first uh, make idea of this in classical mechanics and just copy paste it in quantum mechanics with a little polishing. So I want to talk about Hamiltonian, this thing today. So basically, uh, this Hamiltonian is actually written like this. So imagine you have a particle, just one particle. Uh, okay, let's make everything general. Imagine you have a system. It can be anything, literally anything, which involves motion, which involves movements, which has energies and stuff in that. And so, for a system, you will have variables. So let's say you have these many variables. So these variables will just tell you the values, and these values can change. And then we have corresponding to each variable another variable which will tell dynamics of that variable. So we call this the coordinates, and we call this conjugate momentum, or you can also call this just momentum, generalized momentum. Or so so basically, this can be 1 2 3 4 5. That's why I've written I. This is equal to this. Some math relation. And now let us see. So if you remember, if you have seen it, or even if you haven't, I will still tell that if you have Lagrangian for a system, let's say for this system we have both Lagrangian and a Hamilton. You can think Lagrangian and Hamiltonian as two different machines. Like think think one of them as a gas stove and another one as electric stove. Well, both do the same job but differently. But at the end, both do the same job. Here, both just give equation of motion, same exact same equation of motion. can't have different equation of motion. These are just tools, these are just machines. they, their purpose is to give equation of motion, and even if you don't get equation of motion, at least tell the behavior. Whatever behavior this thing predicts, same behavior should be predicted by this. No, nothing else. So if I have L of a system, I know that between two intervals of time, whatever, if I somehow succeed in minimizing this Lagrangian, whatever trajectory was followed in this Lagrangian. Okay, let me tell again. I should not minimize this Lagrangian. Okay, that was stupid. That was wrong, very wrong. I should minimize this overall integral. I have to minimize this thing called action, and to minimize this, I have to find a path which minimizes it, and this path will correspond to the this path. We believe that this is the path which the particle will take, and whatever path it is, if it minimizes that, because of that path, the coordinates will satisfy this differential equation. They satisfy this. This is what the Lagrangians is. But what Hamiltonian does is the same thing. If again same, again still remember that doesn't matter Hamiltonian or Lagrangian, you have to still use Lagrangian itself to minimize the action. Lagrangian is, I think, the most basic one. Like even Hamiltonian, you have to use. Even for Hamiltonian, you have to use Lagrangian to define it. Lagrangian is pretty. Uh, how should I say? Better, I guess. But now, so Hamiltonian, if it is, if these coordinates, these coordinates follow that path which minimizes the action, then this is how, according to Hamiltonian, this is written. So this is how it's written. So the thing is, here you get n equations, right? Total n equations, because you have n coordinates, and all of them will be a second order. But what we did here is, we actually, instead of n equation, we did a bargain. We said, okay, no, we don't want n equation. We are okay if we get two n equations. So this will have n equations, and this will have total. We will have n equations, and we said, but we don't want second order. We don't want two times derivative. We just want one time derivative. So we just said, so basically you have two n equations in Hamiltonian and first order equations. First order equations to find Q and P. Similarly, here you have here it's you are just finding Q. You are not finding Q dot and all that. You are just finding Q. Here you will find Q and P using these. And actually, okay, I have to be more careful. Q dot. I mean, it is not as easy as I said. I mean, it is not like, okay, you are just converting second order to first order. That's not exactly the way it is. Even if so, you will, yeah, you will surely get like second order to first order. Like you will get first order, but to solve the differential equation, again you have to do tricks like differentiate, twice both sides, like you will get a kind of coupled equations for p and q, and that will have its own complexity. So it's not like you got first order you can solve it. This is just the way we use Hamiltonian. Sometimes Hamiltonian is more useful than Lagrangian, and sometimes the other way around. It just depends on. So if you want to, yeah, what I think is if you want to analyze like many body systems, like for example gas, motion of gas, like you have a lot of particles. Mostly, as far as I've seen, they use this thing. But if you're more interested in just one particle's behavior, like or where it will go, like for example general relativity, or what happens when you have strong gravity, how will a particle, what will the trajectory of a particle in space time, things like that, we generally use Lagrangian. So yeah, it depends what you're doing. And so now, why do I, so let me write that again. This is what it is. This is one of the equation, and the other one is this one. Okay, we were like, okay, from Lagrangian was if Lagrangian is difficult for us, we go to Hamiltonian and reduce our problem. But sometimes we are like, no, we want to reduce our problem further. Then we have another way. If we want to reduce our problem further, we use something called this. We use this. The reason to do this is because the reason to do this is simply search of symmetry. We want symmetry. We just love symmetry. That's all I can tell. That's all I think. It's mostly the reason. There may be other reason, but all I know is symmetry. So what it means is, let me give a example. Imagine you have this. Let's say this is the sun. This is the sun, and there is because so sun is pulling everything towards it. Gravity. Now, if I just have some particle with some mass, if I just place it there, it will directly just sink in the sun. Or if I give it a little push, like if I just give it a little push here in this direction, it may rotate around like this, or just go back in. Depends on how fast I do it. So there are possibilities. Uh, so why am I doing this? The thing is, if I describe uh, uh, so there is a fact that if you have a force like this which is always towards the center of something, it's called central force. And in central force, one good thing is doesn't matter what particle is moving under a central force, doesn't matter how it's moving, whatever it is, from the center, from the center, uh, from where from the center of that force, wherever that force is, all the arrow marks are pointing towards, are coming out from this point. It can be also like this, like in positive charges it is like this, but whatever, if wherever all the arrows are pointing towards, here all the arrows are pointing, like this will point here, 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 all the arrows are pointing here. If you make a line like this, and this particle is moving, after some time it's here. So this, so because of this some area will be formed here. So the thing is, in central force, the area, the rate of change of area, or the area covered from the center, like about by the particle, about the center by the particle at every instant is always fixed. This is just a fact which hundreds of years was verified by a guy called, I think there were many other people, but the most famous guy is Kepler. There is a law which is named after him for this. But in more standard way, we write this thing actually. L is constant, or we can say angular momentum is constant. Angular momentum is not the measure of area getting covered, but uh, angular momentum is proportional to this. It's always constant, and we write it this way. Angular momentum is equal to this is the mass of that particle, that angle it covers every instant per second or per unit time, whatever units we are using, multiplied by the distance from the center square. So the thing is, if this value increases, this will decrease. If this increases, this will decrease. Both just count balance each other out always, such that this overall value is constant. And this does nothing. This is just constant. It's just sitting there unless something is unless the particle is going very very fast, very fast, close to speed of light. Unless that, we are good with this. So now, why did I mention this is, if I write this in uh, the system, polar system, like how far you are and how much angle you are making with respect to a to certain axis from the center, and how far you are from the center. These two numbers you use, you can write angular momentum, but there is also other way to write angular momentum. So Cartesian system, like x, y, any point. So basically this is how it is done, like where you are along this, you just cut here, and then where you are along this, you cut here, you get your xy. And in this the angular momentum will be written something like this. I hope I will do it right. It's very ugly. This is a, but this is equally correct. Mm-hmm. I am just doing some math, don't worry about it. And so this is how it looks. Gone. So in the other system, this is how angular momentum will be written. This is just a different way of writing the same thing. It's like before I was using kg system, now I am using a pounds system, pounds or grams or whatever. This doesn't change that thing itself. It is just a different way depending on what thing it is. So yeah, so one is this way, another is as I read m t this thing. So apparently this is more easy to write and more easy to uh, how should I say find other things using this thing than this thing. It's more, this is more, this looks more complicated while solving problems or while understanding what is happening than this thing. Look, this may be very useful when the force is something like in in this way. Then this will be useless because this is like everything is horizontal, and when everything is horizontal, you use Cartesian, the xy thing. So sometimes we may be needing this thing, sometimes we may be needing this thing, whichever is better for us. So we always require to go from one place to another. I mean, one system to another, and we have to be very good in doing that, which will make our work lesser. That's one of the reason why we use this concept of canonical transformation, reducing our work, reducing the variables. No, you can't reduce the variables. No, but you can reduce the size of equation, and you can reduce your work. You can reduce your calculation steps using this thing. Nothing more than that. Yeah, also using this, it is easy to find conserved quantities. Like you can, to find conserved quantities, you can use this. Like this thing is conserved, like this L is conserved, as I said. Doesn't matter in which system you write, both in both ways it is conserved. Mm, but there are other things similar to L. Like there is this thing called energy, this thing. Then there is this some kind of vector, rung length, we said. All these things are there, and they are also conserved. But you may never be able to tell if it is conserved in one system, because it is very hard to see it. But if the moment you change the system in some other representation, things just become too vivid. It's like many things unravel in front of you, which you never even thought, like, for ages. So yeah, we should be very good in doing all this, from going one place to other. That's why we use this thing called canonical transformation to change this measurement. How should I say? Labeling. We may label a point by x, y, z. We may label a point by r, theta, phi. We may label using what is it? I think it's something like this. No. Yeah, this is good as well. Sometimes we use this instead of this. So no, whatever. So we have different ways to do that. All of them are just as good. All of them are equally correct. But some are more useful than the other in depending on the situation. So let us now see how do we do that. This is the bigger pain, but okay, let's do it. Holy shit. Okay, look, I have a system which has these many coordinates, and each coordinate will have a variable which will tell its dynamics. P1, P2, Pn, and all of this come in very good compact equations, these equations. This is one of them. So I can be 1 2 3 4 until n, and the other one is this one. These are the two equations. And now next is, uh, let's say I don't want to use this coordinate system. I am just like, nah, I don't want to do this. I will find some other coordinate system. I want this, and I will define some new variables. Q, instead of Q, I want something like capital Q. Instead of these P's, all these different weird P's, I want something like capital P. I want these. And so basically, the idea is, okay, I will use J for this. I is reserved for the old system. J, but remember J also goes from 0 1 to n. So every Qj can be written as a function of all this all these coordinates, all these old coordinates, Qi, Pi, and also there can also be time. Yeah, it doesn't matter really. Just let's say ignore this. Okay, ignore this. I'm just using this. If you are not comfortable with it, just set equals 0. Everything will be as if it was never there. It will be just like this, but I will include this as well. It's weird, I know, but you can. And if you think we can't, then just remove it. Just take this is equal to 0, and everything will be the same. Everything will be the way you want. Then this coordinate will also be some function of old. So basically it may have all of these q1, q2, q3. I want to write this. So remember, uh, in this system, the Hamiltonian of this system is k. I mean h. We use this alphabet, right? H. This is the Hamiltonian in this system. Now the thing is, if I in this new system, that Hamiltonian will be represented by some other, instead of P and Q, that will be represented as uh, in Q and P, capital Q and P. So you may argue, so what? This tells energy. Even in other system, it should still be energy H. Just use H. But if I use this T time, I don't know what will happen with this H. So to be safe, I will just write some K. It may be same as H. I don't know. I am just being on the safe side. I just want to write it this way. If we just got at the end K equals to H, then good for us. If we don't, something else, then again good. It's just some equation. I really don't know what learning actually means. Is it just all about convincing yourself after spending hours, or something else? I don't know that. All I know is just I gotta keep moving forward. We have to learn. We have to just keep getting knowledge. I don't know what would I do with it, but who knows. So yeah, so let us do that, such that my new capital Q, I hope I can write it now. This new capital Q, its rate of change can be written like this. I want to do something like this, and that this one is something like this. I haven't done anything extraordinary, nothing impressive here at all, nothing interesting as well. It's just too stupid and boring, but this is what it is. So look at the old equation. Instead of h, I am using k. Instead of small p, I am using capital P. Instead of small q, I am using capital Q. Nothing more or less, that's it. Just change the variables. I want the system to be written in this way, so that hopefully we get some smaller equations, and this will be easier to uh, deal with, and this will be more helpful in understanding that system whichever we are studying. That's why we do this. And now the idea is, there is a thing with Lagrangian, like if with the Lagrangian, if you add derivative of some function of some function of uh, the coordinates you are using in that system and time, then this new Lagrangian which you got can't change shit. This new Lagrangian will still have the exact same equation of motion you had with the old Lagrangian. And the thing is, you can do the same thing with the Hamiltonian. With Hamiltonian, just add again the same whatever you did. But now in Hamiltonian, you can't just add a function of q, but you have to also add a function of p's, yeah, and time. And this can't do shit as well. This will also keep your equation of motion same if you just add this with the Hamiltonian. I am not wrong, I hope. I feel, I don't know, I'm getting a strong feeling I'm wrong here. Am I? Okay, here I am. uh, I may be wrong, there are chances, so let's use a book. So this is a book. So let us see. So as you can see, okay, not this, forget, ignore this. Okay, yeah, see, we will just change the coordinates from one system to another, which we were doing. Okay, good. And then we want something like this, right? Okay, I feel like I'm getting spoilers. No. Okay, that watching books feels spoiler. I don't wanna read books now. Whatever I'm showing, I will show whatever I have in my head at the moment. No books. I will read book later if I want to, and then come back and make a new video. But right now, whatever I have in my head, I will use that. So what should I do? I don't have anything in my head right now. That's all I remember. I think that's it for today. I will, uh, I will become better and maybe start some other day. That's it for now. See ya.